Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Lif Aiman bin Asri. I am from LO1P2. First of all, I would like to thank to my lecturer, Madam Azzyati Johari, for the constant learning at Microsoft Team and the guidance from her YouTube channel on transport principal process. So, let us start with reading the question of mini project on case study about packed tower. Absorption have three stages, which is single stage, multi-stage, and packed tower. For your information, so let us read this question. Acetone is being absorbed by water in a packed tower having a cross-sectional area of 0.86 meter squared at 293 Kelvin and 101.32 kilopascal, which is equivalent to 1 atm. The inlet air contains 2.6 mol% acetone and outlet is 0.5%. The gas flow is 13.65 kg mol inert air per hour. The pure water inlet flow is 45.36 kg mol water per hour. Film coefficient for the given flows in the tower are K prime YA equals to 3.78 times 10 power of negative 2 kg mol per s meter cube mole fraction. Meanwhile, the K prime XA is equal to 6.16 times 10 power of negative 2 kg mol per s meter cube mole fraction. Gradient for equilibrium line is 1.186. So the question is, calculate the tower height using K prime YA, calculate the tower height using K prime XA, and calculate the height of tower using K capital K prime YA. So basically this question wants us to calculate the height of the tower using the different mass transfer coefficient. So let us start with the information that given. Okay, so as we see, the surface cross-sectional area is 0.186 meter squared. So I've jotted down the information here. So as you can see, this is the surface area. The temperature is 293 Kelvin and the pressure is 101.32 kilopascal, which is equivalent to 1 atm. And then this is the mass transfer coefficient. So K prime Y A is for gas, meanwhile the K prime XA is for the liquid. So alright, moving on, we'll go to the packed tower. As you can see, this is the flow for the inlet gas, which is the information that given here is Y equals to 0.026 and V is 13.65 kilogram per hour. And the outlet gas, as you can see, we got Y2 equals to 0.005 and V2 we have to find the value. Inlet absorbent is L2 equals to 45.36 kilogram mole per hour and the X2 is 0. Meanwhile, the outlet absorbent, both information L1 and X1 we have to find for the next calculation. So there are two ways to find the gradient, which is using graph and using the formula on the appendix. So first of all, we must to find X1, which is the outlet absorbent. To find X1, we have to find the formula at appendix. So as you can see, this is the formula. I'll draw for you. This is the formula to find X1. So you just insert the value of L prime, V prime, and x2, y1 and y2 that have been given in the question. So you can put L prime as 45.36, x2 as 0, v prime as 13.65, and y2 as 0.026, 0.026, sorry, and y2 as 0.005. If you calculate it correctly, you will get x1 equals to 0.00648. From this calculation, we can get x1, which is x1 is the point, the first point of the operating line. So as you can see from this graph, I will zoom out. Okay, as you can see from this graph, point 1, we must plot 2 points to find the operating line. And we got here first point, x 0.00648 from the calculation that we calculate just now, and y is 0.026, which is from the question. If you notice, this is the mole of acetone, the percentage of mole, 2.6, and if we divide by 100, we'll get 0.026. Alright, so we'll get 2 points, point 1 and point 2. Alright, so from these 2 points, we can make one line which is called operating line. Okay, and to build another line which is equilibrium line, we must use the gradient that have been given in the question, which is gradient for equilibrium line is 1.186. So from this question, we can conclude that we can use the formula y equals to mx plus c, but we just only use y equals to mx because the c is not intercepting any y-axis. So the gradient is obviously 1.186 for the equilibrium line. So as you can see, we already have the gradient. So to find the point, we just insert 0, x as 0 and y as 0, so that we can get the point. For the first point, is 0, 0, 0 for the first point for the equilibrium line, and insert the last number of your graph, which is 0.02 at the x-axis, and you can see the intersect of the y-axis, which is 0.0237. From this, we already have operating line and equilibrium line. Alright, so next we must find the slope. The slope is as you can see, it is the gradient, decreasing gradient, which is touch the end of the operating line and the middle of the equilibrium line. To find the slope, which is the first trial, we label it as PM1 T1. To find the slope, we also have to find this formula in appendix. So the formula is PM1 T1. T1 refers to trial 1 and M1 refers to the first gradient. M is gradient. So the formula is negative K prime XA, which is we already have, over in bracket 1 minus x1, which is the point in the equilibrium line, over K prime YA, which is also in the, which is already given, over in bracket 1 minus y1, which is the point at the equilibrium line. So we just insert the value that have been given, and you will get the final answer for the gradient of the slope that touching the operating line and equilibrium line is negative 1.6 for the first trial. Alright, and then from this gradient we can insert into the formula of y equals to mx plus c, and you just insert one of the point from the equilibrium line and you will get the intersection. C is 0.0364, which is the slope, which is intersect the y-axis. So from here you can pull out the line by touching the end of the operating line, and you will get this point on the equilibrium line. Okay, so from this point you can derive three things, which is xi1, yi1, and y1 star. How to get x1 xi1 from this point of slope touching the equilibrium line? Just pull down vertically until it touch the x-axis. So this is the 0.013 for the xi1, and horizontally move to the left and you'll touching the y-axis, and we will get yi1, which is 0.0155. Right, okay, so we already have the information of xi1, yi1, and y1 star. Sorry. Okay, so that's the first trial. First trial is basically using the graph. So moving on to find the second trial is using appendix, a formula for appendix theoretically. So to find the PM, okay, this is the second trial, so we label it as PM1 T2, which is stands for second trial. Alright, first of all we have to find 1 minus x in bracket im and 1 minus y in bracket im to find the actual formula, which is PM1 T2. Yeah, alright, so from this formula, to find 1 minus x im, we will use this formula, 1 minus xi minus 1 minus xi1 over ln in bracket 1 minus xi 1 minus x1 over 1 minus xi1. Alright, same goes to the y respectively, just change the coefficient. So you will get I minus x im equals to 0.901 and 1 minus y im equals to 0.979. So from this calculation we can insert into PM1 T2 to find the second trial of the gradient, which is the slope, the gradient of the slope. So we will get negative 1.6, and if we compare the first trial and the second trial, it is just the same. This is just the same. So hence PM1 T1 and PM1 T2 is totally accurate because it is just the same value. Okay, next we have to develop PM2 using, we have developed another slope in the graph by using the information of the first slope, which is M1, and 0.2 for the equilibrium line. So first of all, just use the simple equation of ymx plus c. We will insert the M1 as the slope that we have built just now, and then the point of x0 and y 0.005 is from the point 2. of the operating line. Okay, this one, point 2 of the operating line. Okay, so we'll just insert in the formula of ymx plus c, and we will get c is 0.005, 0.005, and we will mark the point. The point will start here, and then to find the intercept at the axis x, we have to put y as 0 because y is already at this axis, so we must put y as 0 to get the value of x. To get the value of x, we have to put y 0. So if we see it vertically, if we see it horizontally, it will intersect the axis x here. Yes, here. Alright, so from here we can get the slope, the gradient of PM2 is lies on 0.003 and 0 here. Yeah, it lies on here. Alright, sorry for the disruption. Okay, so based on graph, we can find xi1, xi2, yi2, and y2 star, because just now we have the gradient m1, pm1. So the pm1, so from the pm1 we already have xi1, yi1, and y1 star, this one that intersect at the equilibrium line. So this one is for the operating line. So from the operating line, we already have this point here. We already have the slope. Yeah, let me draw the slope. Okay, we already have the slope, and then from this slope, from this PM2, we have to find xi2, yi2, and y2 star. And how to get the value of xi2 is same as the PM1 just now, touching the equilibrium line from the slope. So if you, let me zoom. Okay, if you see here, this is the slope, and touching the equilibrium line, just from the intersection, just pull vertically down and touching the x-axis. So this is the value of xi2, and from the intersection, if you pull left horizontally, we will get yi2. So from the yi2, how to get y2 star? You just pull vertically downward and you will get y2 star here, which is 0, 0 for the y2 star. Alright, so we already have PM1 T1, we already have PM1 T2, we already have xi1, we already have yi1, we already have yi star, we already have xi2, yi2, and y2 star. So what are we going to do now is we already have all the information to calculate the height of the tower. So to calculate the height of tower, we must use this formula for the respective coefficient, and in that formula it is include of xi minus xm. So we have to find this one first. This is also everything formula in transport process is in the appendix. So to find this xi minus x in bracket m, you can find this formula in appendix. So as you can see, this is x in bracket m and y minus yi in bracket m. So these two information of value is needed in the formula for to calculate z. Z is the height of the tower. So as you can see here, we need this value in order to calculate z, which is the height of the tower. So if you calculate xi minus xm using this formula of ln, you will get the final answer for the value of xi minus x in bracket m is 0.00363. Meanwhile, y minus yi in bracket m will get 0.00591. Okay, so combining all the values, listing all the values, we can calculate the height of the tower for the respective coefficient. So what is v1, v2 and v average? Okay, v1 is also the value that is needed in the actual formula to calculate the height. You can find this formula in the appendix to convert the kg mole per hour to kilogram mole per second for the v1, v2 and v average. V average is the average of v1 plus v2 divided by 2 to find the average. Okay, so how do we get the L average? L average for L prime, L1, L2 is all the same. As you can see, 45.36 is already on this question, is stated on the question. Why we divide by 3016? It is because to as I said just now, it is to convert from the hour to second. Because if you look at the question, carefully, it states that this pure water inlet flow is 45.36 kilogram mole water per hour. So we must convert from hour to second. Okay, so we already have all the information. So all we have to do now is to insert the value in the last formula of the calculation. So we start with k prime ya. So this is the formula, V average over S, which is the surface area, cross-sectional area, times y1 minus y2 equals to k prime ya, which is the mass transfer coefficient. This already have at the earlier of the question. The value is already stated at the question. As you can see here, this is the mass transfer coefficient for k prime ya and k prime xa. So all we have to do now is to find the height using the different coefficient of mass transfer. So we go back to the last step. Okay, just insert all of the value to find the z, to find the height of the tower. So from this equation, we have to isolate z at the left of the equation. So it will become V average in bracket y1 minus y2 over S, which is the surface area, times the coefficient k prime ya times the y minus yi in bracket m, which is we already calculate just now. This value we just insert 0.00591. Just insert all of this value in this equation that we already derived, and we will get the final answer for the k prime ya is 1.946 meter. Moving on to the k prime xa, it's just the same. You can find this formula at the appendix of transport principal process, no worries, and just insert all of the value, but this time it's not using the v average, it's using L average, which is already stated at the appendix. So just same as well for the k prime ya, isolate the z, which is the height that we are going to find. Oh, this one it should be over L average times x1 minus x2 over S, which is the surface sectional area, times coefficient times the xi minus x in bracket m. So if you insert all of the value, you will get 1.9631 meter. We already accomplished two coefficient, which is the coefficient k prime ya and k prime xa. So the last one is capital K prime ya. So this one is quite tough because it is a formula in a formula. If you want to find the formula, you have to find another formula to insert in order to find the capital K coefficient. So this is the actual formula. I will mark this is the actual formula to find the k prime ya, because this is the k prime ya, and in order to find the value of capital K prime ya, you have to find 1 minus y star m. So this is the formula, because this 1 minus y star m is needed to calculate the capital K coefficient. So as we can see in this actual formula, the k prime ya you already have the value. Same goes to the 1 minus y im, same goes to the k prime xa, the small k, and same goes to 1 minus x im, and same goes to m prime. We already have all of the value. So what we have to do now, we already calculate the 1 minus y star m, which is 0.983. So we already have the value. All we have to do now is to insert in the actual formula in order to find the capital K. So from this formula, first of all we have to isolate the capital K ya. So you just isolate at the left side of the equation. Isolate at the left side of the equation and just calculate as usual by inserting all of the values. And by insert all of the values, at the end of the calculation, we will get capital K prime ya is equals to 0.02186. Alright. And this formula, V average over S, is to find the height for the capital K coefficient. So this is the capital K. We don't have the capital K. We only have the small k prime. But now we have to find the capital. In order to find the capital K, we have to use the two formula to derive. And lastly, using the formula from the appendix to find the capital K that have Z, which is the height of the tower. So in order to find Z, we have to use in order to find Z for the capital K prime coefficient, we have to use this formula from the appendix. And then same as well, we must isolate we must isolate the z. But before that, I'm sorry, I just missed this just now. Y minus y star in bracket m. So this is the formula in appendix also. We must find this formula first before insert into the actual formula to find the z. Okay, so if you calculate using the formula given, y minus y star in bracket m, we'll get the value, which is 0.01028. Yeah, I forgot to write the final answer for the y minus y star m. Okay, and all of the information is already complete, so just insert the value for the v average y1 minus y2 over s surface sectional area, k prime coefficient, capital K prime coefficient, y minus y star m that we have calculated already just now, and we'll get the final answer of the z for the k capital prime ya is 1.934 meter. So that's it. We already have the k prime ya, k prime xa, and the capital prime ya. So please be sure that the final answer is in unit meter, because it is the unit of the height of the tower. And yeah, that's it. You already have answered all of the question in this mini project. So I hope those who are watching this can understand on this discussion of mini project study case regarding packed tower. And don't forget to subscribe my YouTube channel and give a thumbs up. So that's all from me. Goodbye.